Welcome to the deep dive. Today, we're exploring a really fascinating sequence from the world of numbers, OEIS sequence A000276.
That's right. And for anyone perhaps newer to this, OEIS is the online encyclopedia of integer sequences. It's, well, an incredible resource.
Absolutely. And this sequence, A000276, these are the associated Stirling numbers. We've looked at the OEIS entries, some key papers.
And the goal is to really unpack what makes them tick.
Exactly. So let's get straight to the core idea. What do these numbers actually count? Because they're not just abstract.
Not at all. They count something quite specific. Permutations.
Right. Permutations of n items, but with two key conditions.
Yes. First, no element can stay in its original position, what we call no fixed points.
Okay, so nothing stays put.
And second, the permutation must break down into exactly 2 cycles.
Ah, okay. Can you give us an example? That always helps.
Sure. Let's take n equals 4. The sequence value, A4, is 3.
3. Okay, what are those 3 arrangements?
They are pairing 1, 2, and 3, 4, or pairing 1, 3, and 2, 4, or pairing 1, 4, and 2, 3.
Ah, I see. In each case, you have 4 elements. Nothing is in its original spot. And there are exactly 2 distinct groups, 2 cycles. Like 1 goes to 2, 2 goes back to 1, and 3 goes to 4, 4 goes back to 3.
Precisely. That visual representation makes it much clearer. It grounds the numbers.
It really does. So these AN values are a specific kind of Stirling number.
Yes, they're a type of associated Stirling number of the first kind. The general idea counts permutations where cycles have a minimum length. Here, for A000276, the minimum length is 2. That's the no fixed points part again. And crucially, the number of cycles is fixed at exactly 2.
Got it. And is there a way to calculate them besides listing them all out?
Oh, yes. There's a rather neat formula, actually. AN equals N1 times the sum of 1i, where it goes from 2 up to n down 2.
Wow, okay. A factorial, multiplying a sum of fractions, that sounds like it could get complicated quickly.
It generates integers, but yes, the structure combines factorial growth with this harmonic-like sum. It's quite elegant.
Now, you mentioned structure. I read that traditionally these associated Stirling numbers, when listed in tables, looked a bit messy, like stair-steps.
That's a good way to put it. They often appeared in these staggered arrangements that didn't immediately suggest a simple underlying pattern. It seemed a bit, well, chaotic.
But that changed. There was some kind of breakthrough.
Yes, a very interesting one. Research showed that using a specific mathematical tool, a linear transformation, you can essentially rearrange these numbers.
Like reshuffle them?
Sort of. Think of it like tilting or rotating the way you view the numbers. And when you do that, this seemingly chaotic stair-step structure, it transforms.
Into what?
Into a beautifully ordered arithmetical triangle, very much like Pascal's triangle, which many people know.
Pascal's triangle, that's a huge shift from chaotic stairs.
It is. It reveals this hidden symmetry, this underlying order that just wasn't obvious before. It's a powerful conceptual change because it gives us a much clearer framework to study their properties.
Okay, that's fascinating from a pure math perspective. But you also mentioned their properties are unique, something about Newton-Euler.
Ah, right. That's another layer. Unlike the, let's say, more standard Stirling numbers of the second kind, these associated Stirling numbers, including A000276, do not form what are called Newton-Euler sequences.
And what does that mean practically speaking?
It means they don't follow certain predictable patterns related to divisibility and congruences that simpler sequences often do. Their behavior in that respect is more complex, less straightforward.
So this unique structure, this complexity, does that make them useful outside of pure mathematics? Where might we encounter the need for numbers like these?
Absolutely. Their primary home is in combinatorics, obviously, for counting these specific kinds of permutations and partitions. But that structure has implications.
Like where?
Think about graph theory or network analysis. Understanding cycles and arrangements without fixed points is relevant there. We'll imagine analyzing network robustness or specific types of pathways. You might need to count configurations with certain cyclic properties, maybe ensuring no node just loops back to itself directly. These numbers, with their specific constraints, can model aspects of those complex systems.
Interesting. So analyzing graph properties or network behaviors.
Exactly. Their unique mathematical properties give us tools to count and understand structures that simpler sequences might not capture accurately.
So this journey from messy stairs to an elegant triangle.
It really underscores something fundamental, I think. It shows how a change in perspective, the right mathematical lens, can reveal profound order hidden within apparent complexity.
It's a great reminder that structure can be hidden just beneath the surface.
Precisely. These numbers aren't just disparate points. They're part of a larger, deeply interconnected structure.
And that's a fantastic thought to leave everyone with. Maybe think about other areas, perhaps even in daily life, where what looks like a jumbled set of stairs might actually form a perfect triangle if you just find the right way to look at it. Keep exploring. Keep looking for those hidden patterns.